Now, we haven't talked about an experiment at all. How do we actually know any of these things are true? How does it work out?
Lasers. Yeah,
Lasers? Actually, X-rays. Sometimes lasers, though. Let's talk about structure determination. Yep. So question, how do we know the structure of these solids? So how do we determine that? And I mean it in a general sense. I don't mean a specific. When you're in lab and you say you made something, yeah, you use spectroscopy most of the time. This is a bit different. We're still using radiation, but in most cases it depends on scattering or absorption of stuff. That's where we get into something called diffractometry, which is a fun word to say. But we use experimental or analytical techniques to do that. So analytical structure techniques. There are many different types of structure determination techniques. Which ones are you guys aware of? Yep, X-ray crystallography, which we're definitely going to talk about. What else? IR, yep, infrared. NMR is a big one. Yes, mass spec counts. Pretty much any instrument that we have over there in that other room is used to help you determine structures. So, and you can pair them up with one another. Like you guys said lasers, and I said, sometimes. At UB, they have an X-ray, a single crystal X-ray diffractometer paired up with a laser pulse system so they can study excited states. What they want to try to do is isolate a transition state for the first time ever. So they can watch chemistry happen. Yeah, it's pretty neat. So for now, we're only going to consider two. When we get back to solids, or when we get back to surfaces, we're going to introduce more. Yes, Lily.
Are we going to talk about just IR?
I will actually, Dr. A will probably be coming in to talk about that.
Yes.
So, drift IR will be one. Another one is LEARS. There's a bunch of other acronyms. Dr. Ruprecht, because I can't say his name ever properly. Oh, I meant AJ, but I meant Dr. R. I'm sorry. He does a lot of that. Yep. Jebediah, yeah, he came off the Rumspringer and never went back. That's the. So the two techniques that we're going to consider, which are really important, one, because the mathematics makes a big deal, and it will connect us to the theory that we're going to do in the second part of this class. The two that we will consider first are diffraction or scattering experiments. Some people think that there is a difference between the two. In our situation, we're going to consider them the same. So if you hear a diffraction or a scattering experiment in the scope of this class, they're going to mean the same thing. The two that we are going to talk about are single crystal. Diffraction And then we'll also talk about powder diffraction. Do you guys know what the difference is between these two, or no? Between single crystal and powder. Mhm. Yeah, a powder, you have a crushed up crystal, basically. You want them to be all the same crystal. Doesn't always happen, but you want them to be the same. This is you legitimately have an individual crystal of it. Which one do you think is more routinely used? Powder is. In industry, this is what I did. I never saw one of these until I went to graduate school. Which one do you think you get way more information from? Single crystal, by far. This is like the gold standard of techniques. You do this, you have the electron density, you know what the molecule looks like. It's one of the only ones where you actually can physically use this and see the electron density. The only other one that comes close is STM, scanning tunneling microscopy, but right now with our current resolutions, things just look like blobs. Okay. In these methods, though, they are considered elastic scattering. These methods are considered elastic scattering. What am I talking about there when I say elastic scattering? I need more words. So when you have an elastic collision in physics, what happens in an elastic collision? Yes, energy is perfectly transferred. Nothing is stored. No energy is exchanged. So energy is not exchanged. Is this true? No, it can't be. The other aspect is sometimes you can hit a sample and it will absorb or blow apart what you're sending into it. Okay? That's not what we want, though. For our purposes, we're just going to say everything's elastic. If you care more about when that situation doesn't happen, go to graduate school. Okay. This is used in structure determination. There are people, and eventually we'll talk about a couple of simple techniques that utilize inelastic scattering. Okay. What happens in an inelastic scattering? You have an elastic, yeah, energy is transferred. Is exchanged. Spectroscopy is where this happens. What we generally do here is we're measuring excited states. So what what's the difference between the ground state and the excited state? Yeah, they're not in the lowest energy configuration. Yep. That is for atoms and excited atoms, but molecules and solids do different stuff. Yeah. Okay, let's talk about the general setup for these experiments. Now, Katie, erase this. Yes. Don't, while you're in organic, try not to think about that though. Ignore that. You make Dr. Ogawa very happy. You thought about it not in those terms, but you need to understand those. You need to learn how to drool before you can learn how to crawl. That's the way I'm going to put it. Gotta be able to do the very, very basic stuff before you even touch the upper stuff. It's just the way it is. Okay, general setup for elastic scattering. We usually have an X-ray source. We use X-rays, and we're going to figure out why we use X-rays through some mathematics in a little bit. So why is that utilized? X-rays, oh, X-ray source. It goes in. You have a platform with a crystal on that platform. I'm going to draw this as a single crystal. But it could be a powder. And given its diffraction, what's going to happen to the X-rays? It's going to spread out everywhere. They will be diffracted. Some will make it through, and some will bounce off. And what happens is you will get patterns. These patterns are made when the X-ray bounces off electron density or bounces off an atom, and you will get patterns. And these patterns can be represented from the Miller planes. We'll learn how to do the math and figure that out. But right now, we're not seeing anything. What would we need to see things? Yeah, we need a detector. In the 70s, this was literally film. And when they were studying things in like the 1900s, actually up until the 70s, it was all film. Like, that's what it was. I mean, like physical Polaroid type film. Like it was pictures. And they had to use these pictures to build it up. So I will pass this out, which you're going to need in a little bit, but it shows the workflow. One of them in the corner, and that's labeled figure 5, is actually a single crystal diffraction pattern. And that is on a piece of film. I don't know, I can't remember which scientist it was. I had it written down in here. It was related to the Braggs. They might have even been the Braggs that took that picture. Okay, but to understand what's happening, we have to first hit Bragg's law. Oops, Braggs. I'm not putting an apostrophe here because it's actually a father-son team that determined this. Pretty cool. Okay. Do you guys have any questions about the basic setup of these experiments? What we're going to do next is we're going to hit Bragg's law, because this will be helpful in understanding what's going on. We'll then go into single crystal diffraction. So on that sheet of paper, I have an electron density map, and then I have an ellipsoid picture. We're going to figure out how do we go from these X-rays to that, and what do those things mean? Okay. We really don't have enough time to go into the next bit, but we're going to learn, which way is it? So we're going to learn this and how to derive this, and it's connected to quantum principles because there is a set discrete value that we can have, and that's where that integer comes from. But we're going to pretend that radiation and electrons are behaving as waves only for this first part. We know that's not true, that they behaved as both a particle and a wave, but we're going to use the wave type mechanics to talk about these.
Is that a D?
That is a D. Yep. It has to deal with spacing between lattice planes. Okay? So we're going to derive that. Then we're going to talk about single crystal diffraction. We're going to figure out why are we using X-rays for this stuff. Okay? Are there any questions about anything we talked about so far? No?
No.
Okay. Keep practicing with your Miller planes. The next daily problem will have to deal with like negative values in different directions. Are there any questions right now? All right, have an awesome day.